Hello and welcome to this EFAS webinar on the experimental radar-based flash flood products. All right. Today's content for the webinar, first we'll talk about the motivation of why we have these products and give an overview of the EFAS flash flood products that we have. Then we'll talk about the river flash flood products and urban flash flood products. And finally, we'll talk about the web map service or WMS integration for EFAS. Flash floods are associated with intense precipitation and a less than 24-hour lag to peak discharge. So this is a short warning time and it can lead to a high mortality risk. So our question in EFAS is, can we forecast such events with a greater than 12-hour lead time? We have a long history of working with flash flood forecasting in EFAS, and it started back in around 2010 with the EPIC product, which was based on numerical weather prediction precipitation forecasts. Then in 2015, we released the ERIC product, and this was based on numerical weather prediction precipitation forecasts, as well as the LISFLOOD hydrological model soil moisture forecast. In 2018, we had the ERICA radar-based flash flood products that were released. And then in 2022, the radar-based river flash flood impact forecast products were first introduced as part of EFAS version 4.5. In 2023, the ERIC product was updated in EFAS version 5 to be based on the LISFLOOD hydrological model surface runoff forecast instead of the soil moisture forecast like it was before. And then in March of this year, we released the new experimental radar-based precipitation and urban flash flood products as part of EFAS version 5.4. In the upcoming years, development of the products will continue under the inline project. And then in the future, we hope to integrate the mature radar-based flash flood products into EFAS. The inline project is a 2-year project launched in March of 2025 that aims to improve precipitation estimates and enhance early warning systems during storms, heavy rainfall, and flood events using artificial intelligence. There's 3 main goals of the inline project. The first is to improve precipitation nowcasts and demonstrate them in EFAS. The second outcome is improved visualization of radar-based flash flood products. And finally, the improved inline flash flood notification service will allow users to customize criteria. These new developments are demonstrable in both the dedicated inline web interface as well as through the EFAS development environment. And then in the future, we hope to look into how we can integrate these products into the EFAS flash flood notifications. Currently, we have 3 different types of flash flood products in EFAS. We have the model-based ERIC products, which you're probably familiar with, and these are the ones that we use to send our flash flood notifications. These are based on the LISFLOOD hydrological model. Then we have the radar-based experimental products that we'll focus on today, and these include the river flash flood products and the urban flash flood products. But first, we'll talk about the river flash flood products. These are used to forecast areas which may be affected by riverine flash flooding due to heavy rainfall. And these are developed in the Tamir and the Dera projects. These flash flood products have a 1-hour time step for the first 6 hours lead time, and then a 6-hour time step thereafter, up to 5 days lead time. These forecasts are updated every 1 hour with new radar nowcasts and the latest numerical weather prediction forecasts. The first step in calculating these products is to calculate the river flash flood hazard. To do this, we have precipitation forecasts that are generated hourly by blending the ensemble precipitation forecast inputs from radar nowcasts and the ECMWF numerical weather prediction forecasts. These precipitation forecasts have 51 ensemble members and a spatial resolution of 2 kilometers. And like we said earlier, there's a 1-hour time step for the first 6 hours of lead time and a 6-hour time step thereafter up to 5 days lead time. Using these precipitation forecasts, the rainfall is summarized for grid cells in the LISFLOOD hydrological model for all grid cells with upstream drainage area less than or equal to 1,000 square kilometers. And we do this for the preceding time period of the model simulation that's equal to the time of concentration for the river. Then we compare the summarized rainfall against the 2-year return period climatological threshold rainfall. The second step in generating these products is calculating the river flash flood impact. To do this, we compute the exposure for river grid cells where the accumulated rainfall exceeds the climatological threshold of the 2-year return period. Then we have an exposure layer that's created by combining population and infrastructure data, including data on health, education, transport, and energy generation. Then the flash flood impact level is computed at each time step for each grid cell by intersecting the river flash flood hazard forecast with the combined exposure data. And we get this river flash flood impact matrix that you see in the bottom left. Now we'll talk about the EFAS layers. The first one we have is the radar-based river flash flood impact layer. This shows forecasts with the 1 arc minute river grid cell with drainage area less than or equal to 1,000 square kilometers and the probability of river rain flash flooding that exceeds the 2-year return period threshold. All of these grid cells are categorized according to the impact matrix of the flash flood probability versus the exposure of population and critical infrastructure. And you can see on the right that the animated impact forecasts, you can animate them using the sliders for the 1 by 1 kilometer grid cells. But be warned that the layers may take some time to load because they're still under this experimental phase. We also have the radar-based river flash flood impact catchment summary layers. And these summarize the 90th percentile of the maximum impact level in each subcatchment for the lead time ranges of 0 to 6, 7 to 24, 25 to 48, and greater than 48 hours. So these are a great way to quickly see where there might be impacts at a larger scale. We use the 90th percentile of the impact level to instead of the maximum to avoid communicating potentially misleading the high information to users based on just a single grid cell. So you can find these layers on the flash flood tab in the EFAS map here. If you turn those layers on, you can see a map that looks like this with different catchments, and they're symbolized with different colors according to that risk matrix. If you click on a catchment, then a pop-out window will summarize the impact matrix and different exposure information, such as the total population affected. Here's the suggested workflow for using these river flash flood layers. It can be difficult to identify affected areas using the animated impact layer because the grid cells, which are 1 kilometer by 1 kilometer, are very small when they're zoomed out. So instead, we recommend that you load the radar-based river flash flood impact catchment summary layers for a lead time of interest. Here we're choosing the 0 to 6 hour lead time. Then it symbolizes the different catchments according to the impact. So we can see catchments that are affected. And then we can use the drop-down menus to select the forecast date and time of interest and see where the impacts might be greatest. Next, we can identify a specific subcatchment at risk of being flash flooded. And if we zoom into that subcatchment, then we can switch to the radar-based river flash flood impact layer, which shows us the individual grid cells and their impacts. Finally, we can use the slider to animate the forecast and identify specific grid cells and time steps where flooding is possible. Now we'll continue with the urban flash flood products. The urban flash flood products are nowcast-based products that are used to highlight the risk of flash flooding, and these were developed within the DARA project. First, we have the intense precipitation hazards forecast, and these highlight areas using ellipses to show where the intense precipitation may cause flash flood impacts. The second part of these products is the urban flash flood hazard forecast, which highlight the severity of potential flash flooding in urban areas. The intense precipitation hazard forecasts were developed by FMI, and they combine cell-based storm nowcasts with a machine learning model. In the EFAS map viewer, we use ellipses to indicate where intense precipitation may cause flash flood impacts, and the ellipses are shaded according to the flash flood hazard level. And then finally, the ellipses fade out with increasing lead time to show the uncertainty in the model forecast. Here's a suggested workflow for working with intense precipitation hazard forecast. First, you can select the radar-based intense precipitation hazard layer from the flash flow tab. The second, you can select the forecast from the data options. Then you can click on different dates of interest to visualize the forecast for the next 3 hours. And if you notice that now we select a different time step, that the ellipses have become more transparent due to the longer lead time. The urban flash flood hazard forecasts were developed by UPC, and these combine the radar nowcast with land cover definitions and climatological intensity, duration, frequency statistics. For these forecasts, urban grid cells are symbolized according to the hazard severity, and they have a forecast lead time of 5 hours, with a new forecast generated every 1 hour. These hazard levels, the low hazard level corresponds to rainfall between the 2 and 5 year return periods. Medium or orange is the rainfall between the 5 and 20 year return periods, and red is a rainfall corresponding to a greater than 20-year return period. To use these layers, you can select the radar-based urban flash flood hazard layer from the flash flood tab in the EFAS map viewer, and then select the forecast from the data options and click to visualize the forecast at different lead times. In the final part of this webinar, we'll talk about the Web Map Service or WMS integration. So you can load any of the EFAS map viewer layers into a GIS system of your choosing using web map interfaces or the WMS access. To do this, you can log in through EFAS first. Then you can go to the web services page, which you can find under data access, EFAS web services, and then you'll see a page that looks like this. If you scroll down the page, you'll find a table that has your URL address for the WMS with your personal access token. You need to copy this string here. But be careful not to share your personal access token with anybody. Here we'll give an example using QGIS. If we launch QGIS, then we can right-click on the WMS icon in the browser panel and select New Connection. And this window will come up and we can enter the connection details, including a name such as EFAS. And then under the URL tab, you need to paste the URL that you copied earlier with your WMS access token. Then you should be able to see all the different EFAS layers that you can normally see in the EFAS map viewer. But now you can use them in QGIS. So then you can drag and drop layers from the browser panel to the layers panel. And here we've shown the radar-based river flash flood impact and catchment summary layers. Finally, you can open the temporal controller panel and select a desired time step or animate the different layers. So this WMS integration is really powerful because it allows you to see the EFAS layers in your own system. So if you have your own warning system and you want to see if there's any of these river flash flood impacts or urban impacts on your own system, then you can pull in the data using this WMS integration. Okay, in summary, the radar-based layers provide flash flood guidance up to 5 days ahead by blending radar nowcasts and the numerical weather prediction forecasts. These are updated every 1 hour with the latest radar nowcasts. The Web Map Service integration allows for visualization of the layers outside of the EFAS map viewer. And then these radar-based products are experimental. And this means that they're not supported 24/7, and there could be outages which may only be resolved during office hours. These products will be refined during the inline project, which is a follow-up to the DARE project. And if you're interested in providing feedback and guiding development of products, then you can join the inline community of interest by emailing this email address. So, thanks for watching.